Have you ever stopped to think about what something like a Spotify playlist and the logic inside a computer chip have in common? Well, it all boils down to a really simple idea, just grouping things together. Today, we're going to dive into set theory, which is, and I'm not exaggerating, the absolute foundation for so much of modern math and technology.
So, here's our game plan. First up, we'll get a handle on our basic building block, the set. Then we'll learn the language we need to actually talk about them. After that, we'll see how to put these blocks together in interesting ways. From there, we'll start connecting them using something called relations, and that all leads up to the big finale, figuring out the crucial difference between a relation and a function.
But hey, before we get all technical, let's start with something you literally do every single day. You group things, right? Think about it. Your grocery list, your favorite songs, the players on a sports team, we're just constantly making these little collections, these groups.
Well, in math, the official answer to that question is a set. It's really just a collection of distinct things. And it has two super simple but really powerful rules. First, order doesn't matter. The set with apples, bananas is exactly the same as bananas, apples. And second, you ignore any repeats. So the set 1, 1, 2 is really just 1, 2. That's what keeps everything nice and clean.
Okay, so let's jump right into section 1. What is a set? We're going to get into how we actually describe these fundamental building blocks.
Turns out we've got two main ways to write down a set. The first one's easy. You just list everything out, like we see here with set A. That's perfect for smaller sets, but what if the set is infinite? Well, that's where the second way comes in. You define it with a property. Now that notation for set B might look a little scary, but trust me, it's not. It just means B is the set of all numbers x. That vertical bar just means such that x is a multiple of 3, starting from 0. It's just a rule that spits out an endless set for us, 0, 3, 6, 9, and on and on.
All right, we know what sets are. Now we need to learn how to actually talk about them. So, in section 2, we're going to pick up the language of sets. Think of it as the grammar we need for our building blocks.
And this is where the power of symbols really shines. With just these few little marks, we can say a ton. We can say a number is an element of a set, or that it is not an element of it. We can show that one whole set is a subset of another one, meaning it's totally contained inside it. And yep, we even have a special symbol for the empty set, a set that's got absolutely nothing in it.
So, here's a good question. How do you prove that two sets are truly equal? Well, it's a two-way street. You can't just check it one way. First, you have to show that every single thing in set A is also hiding somewhere in set B. Then, you have to flip it and prove the reverse. Everything in B is also in A. It's kind of like making sure two friend lists are identical. You have to check both lists against each other. Only when both of those checks pass can you say, yep, these sets are equal.
We've got our blocks, we've got our grammar. Now it's time to actually start building. Section 3 is all about combining and comparing sets using our brand new toolkit.
Our toolkit here has 3 essential tools. First, there's the union. That's where we just dump everything from both sets into one big new set. Then we have the intersection, where we're more selective. We only take the stuff that the sets share. And finally, the difference. With this one, we keep what's in the first set, but we toss out anything that also appears in the second one.
All right, let's try a quick one. What's the intersection of these two sets? What's the one thing they have in common? I'll give you a second. You got it right? It's just a set containing the number 2. That's the only element you'll find in both. Simple as that.
Okay, now let's talk about the complement. To get this, you first have to define your universe of all possible options. Let's say our universe U is all the numbers from 1 to 10. If our set A is just 1, 2, 3, then its complement is everything else in that universe that's not in A. So in this case, it'd be 4, 5, 6, 7, 8, 9, 10. It's basically everything else.
This idea leads us to a super powerful rule called De Morgan's Law. It's this awesome shortcut that shows how complements, unions, and intersections are all tied together. For instance, saying someone is not tall or strong is logically the exact same thing as saying they are not tall and not strong. See how that works? It's a neat way to flip your logic around and make complicated statements a lot simpler.
Okay, we have covered a lot of ground with our basic tools, but now we are going to level up. Let's tackle a concept that can feel a little weird at first, but is incredibly powerful. We're going to talk about the set of all subsets.
This thing is called the power set. And yes, you heard that right. It's a set that is made up of other sets.
To build the power set of A, you have to find every single possible combination of subsets you can make from A's elements. And I mean every combination. That includes the empty set and the entire set A itself. You take all those little subsets and put them into one new giant set. And here's a cool trick. If your original set has n elements, its power set will always have 2 to the power of n elements. Pretty neat, huh?
So far, we've just been looking at collections of individual items. But what if we want to start connecting them? Well, in Section 4, we're going to make that leap, moving from simple sets to what are called ordered pairs.
And the main tool we use for this is the Cartesian product. I know, it sounds super fancy, but the idea is actually really simple. You take 2 sets, A and B, and you just create a new set that contains every single possible ordered pair you can make, where the first element comes from A and the second one comes from B. This gives us the entire universe of all possible connections between those 2 sets.
And here's the crucial takeaway from that. A relation is, simply put, any set of ordered pairs. It just defines some kind of relationship between elements. It doesn't have to be all the possible pairs from that big Cartesian product. It can be any specific group of them we decide to care about. For example, the relation is less than would just be a set of pairs like 1, 2, 1, 3, 2, 3, and so on.
And that brings us to our final section. And honestly, it's the big payoff for everything we've just learned. Section 5, Relations versus Functions. This is where we see why this one distinction is one of the most fundamental ideas in all of mathematics.
So what makes a function so special? Well, a function is a really specific, well-behaved kind of relation. It has one single rule that it can never ever break. Every input has to map to exactly one output. Not 0 outputs, not 2 or 3, exactly 1. That's the whole deal.
Let's put that rule to the test. Look at these 2 diagrams. Which one is a function? It's got to be the one on the right. And here's why. If you look at the diagram on the left, the input 2 is shooting off arrows to 3 different outputs. That breaks our rule. That's not a function. But on the right, every single input, A, B, and C, has exactly 1 arrow leaving it. Now, it's totally fine for different inputs to point to the same output as long as each input itself has only one destination.
And this right here is the key takeaway. A relation can be a messy web of connections. An input can go all over the place. But a function? A function is a predictable machine. You put something in, and you know for sure you are getting exactly one thing out. Every single time. That's why all functions are technically relations, but only the most predictable, well-behaved relations get to be called functions.
You know, we started this whole thing by calling sets the building blocks of logic. And we've seen how these incredibly simple ideas about collecting things let us build layers and layers of complexity, from simple operations to relations, and finally to the incredibly precise and powerful idea of a function. These concepts are really the bedrock of so much of our world. So the question I want to leave you with is, now that you know the basics, what will you build with them?